equation up on the board here. 2 sine x equals 1 plus cosine x. That's a little bit tricky because I've got two different trig functions in that equation. And they're not connected to each other by multiplication. They're actually on different sides of the equation. So there's no way I can factor to just break them into separate factors. Okay. What I'm going to do is square both sides of the equation. That's because my Pythagorean identities give me a way of rewriting the square of one trig function in terms of a different trig function. And sometimes that makes my equation easier to solve. So it seems like that's going to make things more complicated, but it's going to allow me to write everything in terms of just sine or just cosine. Okay. Now, I put this note on the board. It says, if you square both sides of an equation, I anticipated that we would be doing that, you must check the resulting solutions in the original equation. Let me just show you why. Let's say I had this equation, x equals -2. Lovely equation, not very difficult to solve, because solving an equation is telling me what value of x would make it true. I'm thinking if x was -2, that would make this equation true. But perhaps I failed to notice that. So I thought, you know what? Let's just square both sides of this equation. It's legal to do that. If this equation is true, this equation will also be true. But if I now go to solve this equation, it has two solutions. X would be plus or minus 2. Only one of the solutions to this equation is a solution to this equation. So sometimes when I square both sides of an equation, the problem is I lose any information I had about whether things were positive or negative. But sometimes the information about the sign determines whether it's a solution or not. So if you square both sides, you will have to go back and check in the original equation. So we're going to square both sides of this. This is the original equation. Anything that we think might be an answer, we've got to plug back in and check. Okay, so I'm going to take 2 sine x and I'm going to square it. And I'm going to take 1 plus cosine x and I'm going to square that. That's going to give me 4 sine squared x. Now I want to remember when I'm squaring this, that just means I've got two factors of 1 plus cosine of x. I don't just square 1 and cosine of x, I square this whole thing. So I'm going to have to FOIL that out. So I'm going to have 4 sine squared x is going to equal 1 plus cosine, that's going to be plus 2 copies of cosine of x. And then my last terms will give me a plus cosine squared. Now if I take a look, I've got cosine squareds and cosines, but I only have sine squareds. So that's the one I'm going to try to get rid of. And I'm just going to use my Pythagorean identity. I know that sine squared x plus cosine squared x is 1. So that means that I can replace sine squared with 1 minus cosine squared. So this becomes 4 times 1 minus cosine squared x is equal to 1 plus 2 cosine x plus cosine squared x. That's going to be 4 minus 4 copies of cosine squared x is equal to 1 plus 2 cosine x plus cosine squared x. Okay, so now no more signs. This is just a quadratic in cosine. I'm going to move everything over to one side and try to set it equal to 0. So I'm going to subtract over the 4, and I'm going to add the 4 copies of cosine squared x. So when I do that, let's come up here, I'm going to have 0 is equal to -3 plus 2 cosine of x plus 5 cosine squared x. Now, I'm going to just rewrite that. I like to have the squared term first. So 5 cosine squared x plus 2 cosine x minus 3. I'm going to hope that that factors. If it unfoils, I would have to, in order to get 5 cosine squared, I'd have to have a 5 cosine x and a cosine x. Now the only integers that are going to multiply to give me 3 are 1 and 3. They're going to have opposite signs, so I know I'm going to be subtracting when I combine my outsides and insides. So let's see. If I put a 1 here and a 3 here, I'd have 15 and 1. I don't like that. Let's try the 3 and the 1. 5 cosines and 3 cosines, yep, those will subtract to give me 2. I want the 3 negative, I want the 1 positive. Let's double check. That's going to give me 5 cosine squared plus 5 cosine x minus 3 cosine x is plus 2 cosine x minus 3. Excellent. So, I've got either that 5 cosine x minus 3 equals 0 or cosine x equals negative 1. Okay, so I got to keep up that original equation because I'm going to have to remember that I've got to plug in my potential solutions to see if they actually work. If I work with this, this would mean 5 cosine of x is equal to 3. So cosine of x would equal 3/5. Okay. Now, that's a positive angle. So, cosine is certainly positive in quadrant 1. The other quadrant where cosine is positive would be quadrant 4. So I'd have to have a reference angle there of alpha. Okay. So, 3/5, not a number that's going to show up in one of my special triangles. So this is just going to be arc cosine of 3/5. And then here, my alpha would be that same angle, arc cosine of 3/5. So this would be 2 pi minus arc cosine of 3/5. Now, notice, in order to be able to plug in to things, I'm going to need to know both what cosine x is. Now, that's pretty straightforward. That's 3/5. But I'm also going to need to know what sine of x is. So, here, I would say sine of arc cosine of 3/5 is, and I'm just going to use the picture. I'm in quadrant 1, so I know it's positive. And then I can draw in my triangle. If cosine was 3/5, then I can solve for the opposite side. So, 3 squared plus p squared is 5 squared. 9 plus p squared is 25. P squared is 16. P is just going to be 4. That's kind of nice. So sine would be 4/5 over here. Now, if this is my x, and I take sine of 2 pi minus arc cosine of 3/5, now I'm in quadrant 4. It's going to be negative, but the absolute value is going to be the same because I'm just going to have this same triangle just drawn over here, so it would be negative 4/5. So let's now check. If I'm working with arc cosine of 3/5 and I plugged in to the left-hand side, I think what I'm going to do is just create a little table here. Here's 2 sine x and 1 plus cosine x. And I'm going to just record what I get if x is arc cosine of 3/5. That was when we said sine would be 4/5. So I would get 2 times 4/5 here, which would be 8/5. And this would be 1 plus cosine in all of these, for both of these rather, is 3/5. That would be 5/5 plus 3/5. That would be 8/5. They're the same. It checks. So this is definitely an answer. Okay. Now, I want to check again. Yeah, with a better marker. Good grief. I want to check again. Oops. Let's keep track of that was negative 4/5. If x is equal to 2 pi minus arc cosine of 3/5. Now, here we said sine would be negative 4/5. So 2 copies of sine would be 2 times negative 4/5, which would be negative 8/5. 1 plus cosine of x is still 1 plus 3/5. That's still 5/5 plus 3/5. That's positive 8/5. They're not the same. Remember I said the problem was that when we square both sides, we lose information about the signs of things? Well, if I squared both of these, they would be the same. But they're not the same. So this is not an answer. It's what we call an extraneous solution. So if we're looking for solutions between 0 and 2 pi, so far we found one. We found arc cosine of 3/5. Okay. Now, we had a second factor. That was a while ago, but we did have a second factor. I think it was, oh dear, let's see if we can remember. It was cosine of x, either plus 1 or minus 1. But let's see, in order to get 3/5, that would have been the minus, so this is going to be the plus 1. So cosine of x plus 1 equals 0 was our other factor. Okay, that's going to mean cosine of x is equal to negative 1. Okay, well that's going to put me right here where x would equal pi. And of course, if x is equal to pi, sine of pi is equal to 0. So let's again create our table with the left-hand side and the right-hand side. If I'm looking at if x is equal to pi, this becomes 2 times 0, which is 0. This becomes 1 plus negative 1, which is 0. They match. Okay. So pi is also a solution. And so then if I want all solutions, I'm going to get arc cosine of 3/5 plus 2 pi n and pi plus 2 pi n, where n is an integer. Okay, good stuff. All right, it's a little tricky, but generally if you see something like this, where you've got two different trig functions and there's no way that you can break them up into separate factors, if there's a Pythagorean identity relating them, probably you're going to want to square both sides. So I'm going to give you another one to work on. We'll end this video here, but before you start the next video, see if you can do this one. It's going to be the same trick, squaring both sides. So let's say tan x is equal to secant of x minus 1. Try solving that by squaring both sides and using, it'll be the Pythagorean identity that gives you the relationship between tangent and secant.